Let's maximize the rate of change. We want to find the maximum rate of change of this scalar function at that point. Now, think of yourself as standing on a hill or some other thing that can vary in two different dimensions. It is a legitimate question. Which direction should you face in order to have your position change the most rapidly? So if you walk sideways around the hill, that means that your level is not changing, and so that would be like a minimum rate of change. But if you walk directly up the hill, then that's when your position might be changing the most rapidly, or directly down the hill. So it's a legitimate question. But also, we have a method of doing this where the direction is going to be in the direction of the gradient vector, and the rate of change is the magnitude of the gradient vector at that point. So it all depends on the gradient. We're going to calculate the gradient first. This is, in principle, it's always the partial with respect to x and then partial with respect to y. If we had a z, we would do that too, but we don't in this problem. So this is partial with respect to x. Well, this part is going to get ignored because from x's perspective, that is a constant. This is going to be 2xy, and that's all. Now the partial with respect to y. From y's perspective, this is a constant. So the derivative of the first term there, the x squared y, from y's perspective, is x squared, the same way that the derivative of like 3y would be 3. X squared is a constant in this from this perspective. So the derivative there is going to be x squared, but then plus the second part, plus 1/2 y to the negative 1/2. All right, what we really need to find is the gradient at this point. So what is the gradient evaluated at 2, 1? Now that we have the gradient as a function, we can put in the x's and the y's. So 2xy is going to be 2 times 2 times 1, and x squared will be 2 squared plus 1/2 times 1 to the negative 1/2. 2 times 2 times 1 is obviously 4. And then this is 2 squared is 4, plus 1/2 times 1 to the negative 1/2. 1 to any power is 1. So this is really 4 plus 1/2. In improper fraction form, it's 4, and then 8/2 plus 1/2 is 9/2. So this is the gradient. Now, keep in mind, the definition of the directional derivative is that it is the gradient dot product, the unit vector that we're wondering about. And then this in turn is equal to the magnitude of the gradient times the magnitude of the unit vector times the cosine of the angle between them. This is from way back from when you first learned about dot products. So now we look at each one of these terms individually. The magnitude of u. U is a unit vector. So this is 1. That means that we don't need to write it. It's not that it's not there. It's that it's equal to 1. And so we don't need to actually write it because times 1 doesn't get written in algebra. Now, cosine of theta. This is what specifies the angle between the gradient of f and the unit vector in which direction we decide to go. In order for this to be maximized, cosine of theta must be 1. And if cosine of theta equals 1, that means theta equals 0. So the direction is the direction specified by gradient of f. The reason this is true is that that cosine term is the only thing that causes this quantity to change. Remember that gradient of f is fixed. As soon as we pick a point, gradient of f is it can't change. So the magnitude of that vector can't change. But what we can change is the angle between this fixed gradient vector and the unit vector, which can possibly point in many different directions. But if we pick the unit vector to be the same as the gradient vector, that's when the money happens. So although we're like picking u is determined by the gradient vector because that's what causes the angle between them to be 0. So we set u to be equal to the gradient. So in what direction does this change occur? It occurs in the direction of gradient of f evaluated at 2, 1, which of course we just calculated to be 4, 9/2. But now look again at the right-hand side of this equation. U dropped out because we know that the magnitude of u is equal to 1. Okay, so we don't need to think about that. Also, cosine of theta is going to be 1 because we know that we're maximizing this thing. Okay, so that is out as well. So now the magnitude of the gradient is the only thing remaining, and it actually can't change. So now we've maximized it by making those choices. And so the directional derivative in any direction we please is maximized when the unit vector is parallel to the gradient. Now this we've already done. And its magnitude at that point is the magnitude of the gradient. So like I said at the start, it all depends on the gradient. So find the maximum rate of change. The maximum rate of change is equal to the magnitude of the gradient vector, meaning the magnitude of the vector for 9/2. Well, now it's just plug and chug. It's square root of 16 plus 81 over 4, the sum of the squares. 16 converted to common denominators is 64 over 4. So this is square root of 64 plus 81 over 4. 64 plus 81 is 145. So this is root 145 square root of 4 is 2. 145 does not simplify because the only things that come out of it are 5 and 29. Neither one of those are squares. So this is the final answer. So just to emphasize and summarize, find the maximum rate of change. It is square root of 145 over 2. And that maximum rate of change occurs in the direction specified by the gradient vector. You can convert it to a unit vector if you want, but you certainly don't have to.